Okay, welcome everyone to the July 20th OMR Architecture Meeting. Today we have one topic on the agenda. So Mark Studley will be taking us through some of the advances that he's been making on JitBuilder 2. So I'll turn it over to Mark.
All right, thanks, Carol. So this is the longest running use of a version number because it's never actually been released as 2.0 at this point, but I have been making some progress on a bunch of different things, and I wanted to give an update to everybody on where things stand because the way you use JitBuilder 2 has changed a little bit in the quest to make it better and easier to use. So I've got part one here because I think I probably have enough content to have an introductory discussion about how things are now working with JitBuilder 2. And I reserved a couple of in-depth topics to do a follow-on. Might be able to schedule it in 2 weeks to do a follow-on to go into more depth on things like allocation and memory allocation and the dynamic extensibility mechanisms. But I will introduce those here in this talk. So, as a reminder, JitBuilder 2 had some goals and there was a motivation associated with it when I embarked on the process of updating JitBuilder to produce a new version of it. Initially, the motivations were around usability because there had been some issues with people using the JitBuilder API and getting confused about it versus the OMR compiler, and it can be more difficult to work with both types of frameworks because they operate very differently. In addition, some of the logging was kind of incomplete with the JitBuilder API just because it was an API, it was a pass-through API, so it was a little bit more difficult to log what was happening, what was going on with the JitBuilder IL itself. So enhancing the ability to log things, debug things, analyze what's going on with at the JitBuilder layer would be nice. Now, following on from that, it also became kind of clear to me that extensibility was a very useful feature, and I wanted to grow that aspect of JitBuilder to be able to make it easier for people to add new types and add new operations, and that kind of translated eventually into my head to I really had to make a new compiler out of this, so it's growing into its own IR, and it has some similarities to the older JitBuilder API that people are familiar with, and the flavor is still the same, but on my path towards enabling easier experimentation and more extensibility and easier extensibility, I've changed things around a little bit and defined a few new concepts, and a lot of it will start looking a lot like a compiler, more like a compiler than the original JitBuilder IL looked like. So, I'm trying to make it much more free for people to try out new things outside of the sort of restrictions of the OMR compiler framing, I called it. So because OMR is used as part of OpenJ9, and it has a very strong use case in that sense, we have to be a little bit careful about how we augment the OMR compiler. This allows a little bit more wild and crazy stuff to happen independently, so we can try stuff out and explore lots of more interesting types of things. So at this point, JitBuilder 2 I'm characterizing as a framework that allows most of its core capabilities to be extended, either statically or dynamically. And I'll talk more about what that means later on. The idea now is that you can plug behavior into JitBuilder 2 as you go. You can create compilers and load extensions that are called as shared libraries, dynamically load them into a compiler instance and use them. And just a point on notation here, so that last word on the slide, which is in red and in the monotype font, that's the notation I'm going to use when I use the actual code name for something in JitBuilder 2 as part of the slide. So just to distinguish it from other words and other uses of things. So when I mean the JitBuilder 2 actual class that's there, that's the notation that I'll use. So you'll see that riddled quite extensively through this presentation. So, and I kind of structured this talk differently than other talks. So I made it into more of a, here's how you use JitBuilder 2 and use that as a framework to introduce the various concepts that I've been working on, as opposed to the, here's how this works, here's how this concept works, here's what this concept is and how it works, etc. So we'll be introducing things as I go. There'll be a little bit of a shock for some of the negotiations and ideas, but I'll try to explain things as I go, and if I miss anything, please feel free to ask a question. So the first basic step in using JitBuilder 2 is to create a compiler object. So if you remember in JitBuilder, there was this init JitBuilder call that you used to call at the, or initialize JIT, haven't used it in a long time. Initialize JIT that you would call, which would, initialize the JIT compiler, and you would then be able to generate code using it. At the end, you'd do shutdown JIT. And there was only ever one JIT. You couldn't call initialize JIT more than once. In JitBuilder 2, you can create different compiler objects, which basically create new contexts to be able to create, incredibly different types of compilers that are operating at the same time in the same process. So here, just to simplify the slides, and I kind of made it clear, everything is in the OMR JitBuilder namespace, but I don't use the OMR JitBuilder namespace anywhere, so please just assume that it's there. The idea is that you can just create a compiler. C, in this case, it can has an empty name, or you can give it a name if you really want to distinguish it from other compilers. When that object goes away, that compiler basically gets completely destructed. So you can imagine that there's like an initialized JIT at the beginning of the first compiler that gets created, and there's a shutdown JIT at the end when it gets destructed, in principle. Although it's not actually done quite that way. Each compiler has an associated config object, which is how you basically configure how it works, as you might expect. So it's got kind of a fluent kind of API there, so you can get the config from the compiler and then set a bunch of things if you want to set things. You can use each one has a different config, so you can configure compilers differently independently, I guess. You can also tailor. There's some things like, for example, if you want to provide a certain kind of allocator, like a tracing allocator, when you create the compiler object itself. So if you want the memory allocator that the compiler is going to use to be a tracing allocator, you have to set that up when you're creating the compiler. And so that's something that you can do in a config. You can create a config option, config object yourself, configure it in however way you want, and then pass that thing into the compiler object that you create, and it will use that config object. I've mentioned allocation here. So dynamically allocated memory is managed separately for each compiler. So it purposefully keeps the allocations separate for each of the compilers, so they're completely independent. Although there is a way to establish a parent-child kind of relationship between compilers, so it's possible for a child to refer to a parent's memory, but the allocation is controlled specifically by each compiler object. And you can very easily ask a compiler for its allocator so that you can allocate objects that have the same life cycle as the compiler. And just like in Testarossa, once the compiler goes away, all its memory goes away as well. That's the principle anyway. It's not actually how it works right now. Right now, the allocator is just calling malloc and free, but but all of the objects within JitBuilder are using the allocator API to allocate memory through that API. So eventually, it will do the thing it's supposed to do. I'm not going to talk again about allocations specifically in this talk. It's a part 2 topic to be expanded upon later.
Can I ask a question?
Yeah, sure.
Yeah. So for the configuration objects, what do you have in the configure? What can you configure?
Not very much right now. It's mainly just a principled concept, but it does have some things for specifying tracing. It does have there is some basic support for like perform transformation and being able to turn certain transformations on and off, that kind of thing. There aren't very many things that use perform transformation yet,
okay. But you can you define the JIT command line?
No, no, it doesn't have anything like that. So the
JIT options.
The idea for command line processing. So I mean, if you use the OMR compiler under the covers, obviously it processes TR options and does whatever it wants. But for the JitBuilder 2 config itself, the idea would be that eventually, it doesn't do this now, you would write your own command line processor, which would translate your command line options into the command line, the config object. And then the project might provide a default implementation of a config that has a particular notion of what command line options look like. So if you want to use that, you can use it. But otherwise, if you have an existing runtime, say, where that command line option scenario doesn't work, then you can do your own. You can roll your own. That's the idea anyway. That's all conceptual at this point, but that's the basic idea.
Okay, thanks.
One question before you go, is the plan later to use the OMR memory stuff, or just you want to keep JitBuilder's memory allocation separate?
It could. There's no reason why you couldn't have allocators that reuse the OMR ones if you wanted to. But I'm keeping it separate for now because, so one possible wild and crazy direction here is that JitBuilder 2 becomes the compiler implementation, so it subsumes the OMR compiler. There are other things like you could very easily make an LLVM code generator for JitBuilder 2 right now. Like it's not it doesn't have JitBuilder or OMR compiler baked into it on purpose. And actually, I'll talk a little bit about that when I get to extensions, but not a lot. All right, so compilers can compile things. That's a very useful statement. But the things that get compiled are anything that subclasses a thing called compile unit, which was kind of the most basic name that I could come up with it. I didn't want to use unit because it was too generic. So compile unit, you can think of this like functions or traces or basic blocks or funcs or helpers or bytecode hunt, whatever unit of compilation you want to have, you can, in principle, create a subclass of compile unit to handle that. And then how it's compiled gets described by a thing called a strategy, which has a strategy ID. All of these things have IDs, actually, but a strategy ID that you can pass around, and then you can request that you compile a compile unit using that strategy. So this code here shows the basic process here. You create a compiler, you create some kind of compile unit, which obviously this is very generic. You can't actually allocate a compile unit. Like you can, but it's not very useful because it doesn't do anything. And then you get your hands on a strategy ID from somewhere. I'll talk a little bit about that later. And then from the compiler, you can ask it to compile the compilation unit using this strategy. And then if that was successful, then it's great. If it wasn't successful, you can deal with the failure. Hold your questions about that section of code just now, because I'm going to go through a few points on it. Once you've done the compile, it creates a thing called a compiled body. Everyone should recognize these names from Testarossa world, or just compilers in general. It creates a compiled body object, which is associated with the strategy that was used to compile it, right? So in the OpenJ9 world, this would be a cold or a warm or a hot strategy would be used to compile some Java method, and you could ask for the compiled body for that method if it was cold or warm or hot or whatever. They don't replace each other. You can have multiple compiled bodies stored on the compile unit. And then each compiled body can provide the entry points that you need to access it. So this is quite sort of similar to how you would have done this with JitBuilder 1, but you can ask the body for a native entry point. And then this is kind of an example of how I have used templates throughout JitBuilder 2 as kind of a way of avoiding having static casts all over the place. You basically provide a type, and that type gets hidden within this function thing. So you just see a native entry point of a function prototype thing, and it does the cast for you. And occasionally other things as well. Like there's other code that gets hidden behind this kind of template notion, but you'll see this in a number of different places. And then the idea is you can just call F, like that's a C function in this particular case, right? Because you've compiled it in some way. All right, so there are some things in here that I didn't talk about very much. So let's go through some of them. So compile unit is obviously a very generic class. It's not very useful. In fact, if you do actually allocate a compile unit and try to compile it, it won't do anything because it doesn't generate any IL. It doesn't tell you anything about how to compile anything. It just it has like return true basic elements to make the compile succeed, but it doesn't actually do anything. So you need to add new kinds of compile units into JitBuilder 2 using things called extensions, and I'll talk more about these coming up in a little while.
Compile unit analogous to the method to be compiled?
Yes. Okay. Yeah. I think of it like it's like a TR method, right? But it could also be a J9 method. Like it's basically just a thing to hang on to the things that you want to compile. And then, so extensions are able to, so there's ways in JitBuilder 2 that extensions can add new compile unit types, basically just by subclassing. Extensions can also add new strategies if they want to do different types of compiles. If, you can have a compile strategy. The only compile strategy actually that JitBuilder 2 defines is the codegen strategy, which basically just does codegen, doesn't do any optimizations. But you can define new passes. You can add those passes to strategies. You can define what those strategies are called and register them with the compiler, and then you can use your compile call to cause it to use that strategy when it compiles a particular unit. You can add new compiler return codes. So there are a few that get defined by the compiler itself and they're accessed off the compiler object, but you can also create your own, you can register your own compiler return codes so that code can depend on those return codes. There's also, it uses exceptions to handle exceptional conditions, and then you can define new types of compiler exceptions that can get passed in, et cetera. And all of that stuff gets handled by extension objects, which I'll, again, eventually talk about. But just trying to give you a flavor for how these things get tacked in. There's also this loc thing that's sort of sprinkled through here, and you'll see it sprinkled through a number of the examples that I've got in here. So this is, I'm going to talk about this one in a little bit more detail. I have a whole slide dedicated to it. So many of the objects that get created in JitBuilder 2 get tagged with their creation location. So this is really a debug feature, trying to aid in being able to associate specific objects with where they got created. And the reason why I thought this was even more important to do than in other compilers is because if I'm designing an extensible code framework where you're going to be reusing other people's extensions to complete a compiler, you may have no idea where a particular thing actually got created. And so having a way of tracking where things are and who was creating them and what line of code actually produced this thing is actually, you know, I considered that to be a very important feature here. So loc is just a preprocessor macro that expands into the usual three arguments that locate where things are, which file you're in, which line number you're at, and which function you're in the middle of. And then there are corresponding macros that allow JitBuilder 2 functions to kind of pass those things around. So you can accept a location as a parameter in a function to force somebody to pass in one of these things. If you're a JitBuilder 2 function that needs to call something that's going to allocate more stuff, you can pass the location through so that it goes all the way out to the code location that's outside of JitBuilder 2, right? So you don't see all of these things being created by JitBuilder 2 itself. You pass through the caller context basically, so you can see where it got created from. And then many of the constructors, especially in the IL elements, are taking a location as their first parameter, so that it can be tagged by the call into JitBuilder 2 that caused it to get created. Now, I'm pretty sure everyone on the call is kind of twisting their mouth and it's unpleasant. I guess this is. I think it's going to be very useful for debugging, and hopefully it outweighs the pain. There are some very non-ideal aspects of this, like for instance, it's the first parameter and there's 3 of them, so it kind of uses up a lot of the registers that you might otherwise use for passing things around. So it'll probably have some performance impact. It does clutter up the code a little bit. I tried to keep the one that you use most frequently, which is on the caller side, the loc, as the shortest possible thing that I could get. But it does kind of show up in a lot of places, and it does kind of clutter the code up a little bit. I am open to alternative suggestions if people have other thoughts for better ways to do this, but it's the easiest thing that I could come up with, and I've been doing this fairly consistently since I started. So pretty much everything in the compiler right now does have this sort of this use of location and loc, and it's there, and you know it's relatively easy to expand it with new code that follows the same guidelines basically, but. Like I say, if there's other ways of doing this that are better that I haven't thought of, please suggest them, because I'm not super happy with it.
Is there the notion of an unknown location? Like, one example I'll give you is that one of the projects that I worked on, I have no idea where the came from.
Yeah.
So I would just make up -1 for the line number, so I know that, or make up a bogus name.
Yep.
But is there the...
Well, I mean, you can always just pass in the location that you're, like the call that you're on, right? This location is not necessarily the location of the source code line of the thing that you're compiling necessarily. It's more of a where in the compiler's source code did this thing get created, right? That other thing that you're talking, or that other notion of the source code line, that also exists. There's a thing called source location that you can specify as an operation. It's actually in I believe it's in the core extension that you can basically tag. It's like an operation. It says from this point forward, this is the source code location, and it has this similar kind of things that you can add into it, like a bytecode index and a file and such and so on. And then when we compile that down into the OMR compiler, it basically makes up bytecode indices to correspond to the source code location. So it does track all the way down. It just, you have to munch things a little bit because the OMR compiler doesn't have a super generic notion of what a location is. But the idea is that at the JitBuilder 2 level, you have a set of source locations that you know about, and you associate them with bytecode indices at the OMR compiler level, so you can track, you can figure out, basically map how it works together. Okay, and so I didn't talk very much about what goes into a compile unit. I mean, you can kind of imagine this, but here's the sort of one slide summary of the IL, which obviously isn't a lot of detail. So, but most of these are things that I think will be familiar to people who've used JitBuilder before or who've worked on compilers before. There are a couple of interesting ones that I'll spend a little bit of extra time talking about. So we've talked about compile unit already. The two new ones are this top level scope and context objects. I'm going to just defer that for now. Like scope is kind of associated with the code and context is sort of associated with data, but just suspend those for a minute while I talk more about, well, I guess I'm going to talk about scope right away. Scope is really an abstraction layer over the flow of control to builder objects. That's a really weird statement, but basically it provides a way for the compiler to talk about code that needs to happen when you move between two different builder objects. So the example that I think I want to use for this one, and let me know if it doesn't make sense, would be, imagine that you're compiling in a secure environment and you've got code that has two different security domains. The code for each of those domains would be in different builder objects in principle, right? And if you wanted to transfer control from one to the other, there might be things that you need to do in order to get out of one context and into another context. So the scope object can be used to represent that kind of relationship without having it have to be reflected directly in the IL of the code you're compiling. So basically it provides a way to it's like an abstraction layer. It allows the compiler to see the operations that are actually being performed by the code without necessarily having to see around a bunch of other stuff that's there to manage things like moving between security contexts.
So it's a bit like a glorified linkage.
In a sense, yes. So I'm not going to talk about this very much in this talk, so I don't want to get stuck here. And it's also, like I said, I haven't really thought very hard on how to explain this to people. But I did want to mention it just because it's a new thing that got introduced. And context is kind of the same flavor, but I'll talk about it later. It's the same thing for symbols. Anyway, builders. Let's get back to something more basic. So builders are basically a sequence of operation objects. They're not basic blocks. They're single entry, and they can have multiple exits. They can also have internal control flow, but it has to be completely contained internal control flow. And that internal control flow has to be sort of managed within an individual operation. So the best example of an internal control flow is an if-then-else, right? So it has an embedded split and merge. It's all contained within the if-then-else operation, but it references other builder objects for holding what has to happen on the then side, what has to happen on the else side, and so those are sort of builder objects that are referenced from inside the operation, and that's what I kind of got ahead of myself a little bit, but operations are what we use to describe some action like add or load, or for loop is another example of something that would have an internal control flow because it's got a body of a for loop, it's got a break label that you need to jump to, it's got a continue label that you might need to to jump to. And so the builder objects that are referenced from an operation can be either bound, in other words, they're reflecting this internal kind of control flow, like the body of a for loop, or like the then side of an if then else. Or they can be unbound, as in other words, they're just a pure outward flow. I'm just going over to that other builder over there, and there's no relationship. I'm not going to come back into this builder from there. So an example of that would be something like an if compare equal to. If they're equal to this, then go branch over there, and you're not going to come back. So these notions are kind of encapsulated in how builder objects hold things in operation. So they're a little bit more powerful than a basic block, but they're not completely strange.
How does the loop work in terms of the fact that there's technically two enters, right?
technically 2 enters.
So when you have an edge going back at the start, there's one from the previous block and then one from the end, right? So how does it deal with that?
So the for loop itself has an entry edge that gets you into the for loop, and then there's an exit edge from the for loop ends at some point, and that's after you've finished executing the for loop. And then as you're executing the operation, the for loop operation, it's managing run the builder thing, run the body loop, do the test. Is it done? Do it again, right? It's managing that control flow. So it basically handles the flowing of stuff around when the builder gets it's a little bit complicated, but it's also quite regulated as well. So it's not as bad to deal with as you might think.
So in this world, then imagine like a builder is composed of normal operations that you would imagine in a basic block, like adds, subtract, stores, loads.
Right.
But then also interspersed amongst those is sort of these macro level operations.
Correct.
Like if then else with builders on both sides. And then after that, you can continue on doing simple operations like load and store.
Right.
So all that would be within one builder
object.
Object. Yeah.
Right. So it's a nested IL for sure. It's not a sort of like if you look at like Testarosa's IL, for example, the arrangement of blocks, they're all very linear on purpose, right? There's no multi-layers, right? It's just a simple list of operations, and if there's an operation that's control flow, that's the end of the block, and you're done, kind of, right? But we've used that to do, we put those blocks together in Testarosa to do like methods full of like a compile unit that's a full method. We've used it in ZPDT, for example, to do build traces where it's a different sort of arrangement of things. Builder is just a slightly more powerful way of assembling operations, and they make it, in my opinion, anyway, they make it a little bit easier to do extensions that can create fairly powerful new operations that in pretty general ways.
Yeah. So, and the reason I ask is we don't have to linger on this point much, but in the Java side, recently I was thinking about the effect that certain guards have on the IL, and like in particular OSR on stack replacement, breaks blocks, and requires GRA to pass values between blocks. And thinking if there was a nice way to just encapsulate all that in place in a tree and have it almost be expanded by the code gen, not break a block whenever you insert one of these guards.
So that sounds more, what you just described, at the level that you just described, it sounds more like a scope thing than it does like the builder thing in itself, right? So scopes, like I mentioned scope as a, like compile unit has a scope, but you can have inner scopes, you can have nested scopes, you can have object, like builder objects. Basically a builder object has a scope that it links to, and then you can have a number of builders that have that scope, and the builders themselves don't necessarily have to be a structured control flow kind of thing that can come from anywhere, right? The easiest thing is like an inline scope, maybe, right? Like the inline body has its own scope, and the caller has a scope, and all of the code that's associated with the caller can have the caller's scope, and all the code that's associated with the inlined code could have an inlined scope, and those objects can have different things. But in your example, you could have a scope that captures what is the code that's covered by this OSR guard, and then talk about what has to happen if you come out of that section via a particular exit, say.
Right. Okay. I mean, yeah.
Yeah, we can talk about it in more detail another time, maybe, because I don't want to get stuck here for too long. All right, so let's move away from builders. Symbols. So symbols don't exist in the JitBuilder API, but they do in the JitBuilder 2 world. So because they become easier ways to reference memory. Obviously, they exist in the OMR compiler, and they represent different types of memory that operations can access. Values are they're sort of the same thing that existed in JitBuilder as a way of passing operands around between different operations. Conceptually, I guess you can think of them sort of like local variables, but they're not necessarily local variables. They could also you could also be think of them as an infinite virtual register set, but they're not necessarily registers. They're just ways of passing values around. And then all values and symbols have types, so you can ensure type safe access for all of these things. And then context. So context is similar to scope, but for data objects. And the reason why I designed this context notion was so the entire compile unit can have a context. Again, there can be inner contexts, but it's a way of abstracting away how the function or how the compile unit accesses symbols. And the motivating reason for this, which I think is a generic kind of use case, was actually in the debugger. Because in the debugger, when I was building the debugger, it basically takes the whole set of the frame, the parameters and the values, and says, well, they're not actually in those places directly on the stack frame. They're actually being maintained in this array of debug values that the debugger is maintaining outside of the native code that you're generating. And so this context layer provides a mechanism whereby you can the code can say, I need to access this symbol, and when the context can provide the IL that's needed in order to actually get the value of that symbol from a particular element of the context, like the debug value sitting in an array based on the number of the value or whatnot. Again, that's probably too abstract for this conversation, so maybe I'll also defer this to a later discussion. All of these things, other than the compile unit, which is something that exists outside of a compilation, all of them get created inside a compilation. So there's a memory allocator that's associated with a compilation object, and it's the thing you should be using to allocate all of these things, and that's basically how JitBuilder 2 is set up to do this. And that had some implications for how you actually write the code that you use to specify a compile unit, like a function. So I think, yeah, so the next few slides, I'm going to revisit one of the basic examples that I've used to talk about JitBuilder in the past, which is generating a function that just increments a 32-bit integer value. So if you wrote that code in C, it would look like this, with the int32t being returned by increment, takes a value in, it just returns value +1, right? It's a little bit more complicated than my return 3 famous example, but it's not very much more complicated, right? So this example that I'm going to go through is specific to handling a 32-bit integer type, but it should be fairly easy to see how you could generalize this for any numeric type quite easily. The basic process here, which is the same thing that you had from JitBuilder, is it's just the names are different and the fact that there's a compiler involved. But you write a subclass of compile unit that knows what kinds of things the function should do and how you should pass in value and what you're going to get back. Then you allocate an object of that class which corresponds to this increment guy that you're trying to compile, and then you ask a compiler to compile it. And then the thing you get back, you can call that just like you'd written this source code in this on the slide, and pass it a value. So we're building a function. So functions in JitBuilder 2 are supported by an extension called func, just because function was too long. So the way that you get access to a func extension is there's a particular header file that basically it defines everything inside this namespace func that tells you how to use what you can do in functions. There's also another extension called base that gets used in this example, which provides all of the IL support that's kind of like what's in JitBuilder. So by default, I think I mentioned before, JitBuilder 2 doesn't really have very much itself that you can do with it. You have to load extensions to provide things that you want. So the idea here is that you don't have to use functions if you don't want to use functions. If you're building a trace JIT that works with traces, you just load a trace extension. You wouldn't have to have the functions extension present loaded, taking up memory, taking up space in your cognitive brain, whatever. And base is an extremely poorly named extension that just provides a lot of like add, sub, load, store, or not even load store, support for structs, support for pointers, things like that. And then, so in terms of kind of getting going, again, I'm going to use using namespace func. I don't actually recommend doing this, and I don't do it in any of the code base anywhere. I use more like this base extension notation here to add the namespace all the time, which is why I like a short namespace name. But you create a compiler, and then you can load an extension very easily just by giving the name of the function extension class, which is there actually is an object called an extension object, and you give that object name, and it will go and load it. It knows what its name is. From a name, it derives a library file name to load dynamically off disk, and it goes off and finds it. And it hands you, as part of loading that thing, it creates an object of this type, and it returns it to you. And then you use this function later on to do all the kinds of things that the function extension allows you to do. And in some cases, you can refer to classes that are also loaded as part of the function extension. And then the same thing you can do for the base extension, right? In this case, you just create the base extension object and load it, and the compiler will load it and give you an object back. Obviously, there should be error checking here, but it's a slide. This kind of notation FXBX is, again, it's because you see these quite a lot in the code, I tend to use very short names for them to try and distinguish between them without creating a lot of visual clutter. Now, func introduces a function class, which subclasses compile unit. So now we can create functions to compile. And the expectation is that that's going to be further subclassed by some compiler environment to create specific functions. So in this case, it's like the method builder that you had in JitBuilder, except that now function is not itself a builder object. So it used to be the case that you created a method builder and you could already just add operations to it, and you'd be adding operations to the code path that gets called when you call the function. It starts off executing those operations. However, now, because I didn't want to make builder or compile unit sort of cross-connected, function is not a builder itself, so you have to do something else, and I'll talk about what that is later. In JitBuilder, there were basically two things that you created. You created a constructor that would tell you about what the function did and how you would call it, and then build.il you would define to build the IL, which described what the function actually does. There are now 3 in JitBuilder 2. One of them is the same constructor, but you can't do as much here because more of the, it's hard to describe parameters because you need types and you need symbols, and those things are only supposed to be mostly created inside a compilation. You haven't started a compilation yet. You're just creating this object to be compiled. So those two things have been kind of split out. So now there's a constructor where you can do a little bit of stuff, and build context is something that now gets called before build.il in order to build out this notion of what the function is that you're actually calling. And then you still have to do build.il. Build.il used to be a parameterless function. Again, because it was a pass-through API, it was a lot simpler to work with. Now you kind of need access to a compilation object, and I've also augmented that with passing in a context and a scope object. Technically, these things are accessible from the compilation. You can do comp arrow scope and get the scope object, or arrow context and get the context object. But for simplicity, I added these as additional parameters, and again, it just kind of reduces the boilerplate that you commonly need when you're writing these things. You'll see examples of that later on.
What's the difference between C and comp? Like compiler and function compilation?
When you see C, it's usually the compiler.
Which is when compilation is the TR compilation.
Compilation is like TR compilation. Okay. Yeah.
But like so
compiler is like TR. It's like everything, right? We don't actually have a TR object that corresponds to the whole compiler, but if there was one, that would be compiler. And then compilation is like TR compilation.
Is it extending?
No.
OMR compilation?
No.
Oh no.
No. None of this code has any dependency on OMR compiler. So it's all completely separate. But I'll show you how JitBuilder, how it gets into the OMR compiler later via JitBuilder, but it's the same basic principle. Right, okay, and then another common thing that you see when you have to do these is to, because extension objects are used to produce IL, you kind of want to have these objects around readily accessible. So I often produce them as fields on the object, right? So there's a core extension I'll tell you about later, a function extension, which I just mentioned, base extension I just mentioned, right? So stored on the six. These basically is what the constructor is going to set all of these things up and remember them. And then I also sometimes pass around symbol, hold the symbol so that it's easier to remember the information that you did in build context and have it available for you in build IL very easily without having to look it up. So,
are you going to explain it? Oh, maybe we'll have it on the next slide about how the extensions are loaded?
I'm not going to go into detail on that.
Where are they coming? Because there it's just saying C-load extension.
Yeah.
So
function extension has that class has a name. So that class is going to get embedded into your whatever your context is, and it has a static name option or a name field that has the name of what that extension is called, which gets pulled out, put into a call to loads a static library that has that name on disk, and then it pulls that in, and
so there's a library load in
right,
the background,
and then it calls inside. Once it loads that library, it looks for a create function that it can pass in the compiler object and some other stuff, and it calls that, and then that create function of the extension actually creates the function extension object that you're going to use, and it returns it basically, and then that lets you get access to all of the functionality that's inside the extension. Okay, so the constructor executes outside of compilation, so you can't do anything like build IL or create symbols. So it's a little bit simpler than it used to be in JitBuilder, although it does also sort of create all of these little cached things for later use mostly in build IL. These are the ways that you can get access to various extension objects. So this is core extension is something that gets created by every compiler. So every compiler creates the core extension and has it sitting there, so you can just ask for it. There's not very much in here. I'm not going to talk very much about it. It's some very basic stuff like create an orphan builder and things like that. And then if an extension has already been loaded, you can call lookup extension, and it will go and find the object for you. So the compiler knows how to find the extension object for a particular type 2 if you want. So rather than go through the whole load process again, it just looks it up in its little list. And then the value parm gets initialized to null initially because it hasn't been defined yet. And then the only thing that you can really do in the constructor is you can define the name of the target function. And just like in JitBuilder, this has very little actual value in terms of how the code gets generated, but it's useful from a debug standpoint, so you know what thing you're talking about. Build context and build IL both run inside compilation. These should probably be in red, but anyway, just keep my notations consistent. But anyway, so I'm going to talk about both of these in the next few slides. But at a high level, basically, build context is supposed to describe how the function interacts with its environment. So for functions, it's define what the parameters are and what the return type is going to be. In build IL's case, it's supposed to describe what the function does when it's called. So that's going to build the IL, not build the IL, it's in the name, and how it's going to compute the values that it will return. Could have come up with a better title for this. So here's the code that we've got inside build context. So the JitBuilder code for this basically looked like define parameter value with int32 and define return type int32. So it's not much more complicated than in the JitBuilder API here. I've shown how you can get a type. So again, types aren't actually, that's almost true. There are almost no types that are defined by default by the compiler. There is actually a type called no type, which is kind of like void. So not very useful, but it's there. And then extensions can add their own types. So when the base extension gets created and loaded, it allocates a number of types, and it makes them accessible directly off of the object here as the primitive types. So these are the same primitive types that are familiar from JitBuilder world. There's int 8, 16, 32, 64, float. I renamed float and double to float 32 and float 64 for consistency. There's address as well. One thing that's interesting about types is that they're always const. so you can't change them once you've created them, which makes it awkward to pass them around sometimes, but we managed to figure it all out. The usual C++ const issues. Right, so here we've just said the parameter type that we're going to use is int32, and then we have to define a parameter, which we do on the context. We tell the context that there's a parameter to be defined. We give it a name and what the type is going to be. So this is almost exactly the same as what we would have done in JitBuilder, the API. The only difference is it actually returns a symbol that corresponds to that parameter. So there's another thing that the base, or actually that the function, if the function extension creates, is a parameter symbol type that you can store there. And then the other piece is the return type. So it's going to return the same parm type, and it's the context that knows about all of this. If you had multiple parameters, you can call define parameter multiple times. It assumes that in order you're calling them from left to right. So it's relatively easy to do that. Wouldn't be hard to change this so that you could do it in random orders, but in principle, this usually seems to be good enough. All right, so that's build context. Oh, look at that. Right, so I think I said all of this stuff right. And right, okay, so build IL. Let's get into actually building the IL now. So the first thing we need to do, remember I mentioned that in JitBuilder, method builders were builder objects, so you could automatically just put code into them. And functions are not builder objects, so we have to find a builder object to put this in. And so the first thing we do is ask the scope, which got passed into us, for an entry point. And there are different kinds of entry points that can be stored here, but builder entry is sort of the one that's always there it's the one that's commonly used when you're building IL. And you can ask the builder entry for its builder. So this is, again, that same kind of notion that I said before, except this one's actually doing it's doing more work than just casting. It's actually looking through a list that's dedicated to entries of entry 0 to find an entry point that has the type of builder entry, and it will return it if it's got it. So again, should be error checking if it's not there, etc. But this is just a slide. And then builder entry is really just a class that holds onto it's an entry point that holds onto a builder object for you, so you can ask it and get it back. So now we've got entry. This is the place where this is the code path that corresponds to somebody called this function, and this is the code that's supposed to execute. Right. And there can be other kinds of entries, like for example, at the end of compilation, the scope will hold native entry points because the code gen will have generated code for it, and it will have a native entry point associated with it, which then gets transferred to the compiled body at the end of the compilation. All right, so once we have the entry builder, then we can start doing our code. So that looks like this. It's very similar in nature to what you would have seen in JitBuilder, but it's actually different. So I just wanted to call out and simplify it a little bit. So the red bits here are basically just showing you the structure of the computation that you're doing. You've got a value that you're loading, and it's being stored into a value T1. You have a constant integer, 32-bit integer for the number 1, which is being stored into T2. You're adding those together and then taking the product of those, the sum of those, which is stored in T3, and returning it from the function, right? So that's the basic structure of this. But there are some elements here that are different. Right. So let me just step away from it for a second. So the generic way that you added operations in JitBuilder was you got some builder object somewhere, and you called builder arrow the operation that you wanted to do and passed it operations, and that would hand back, if it produces a result, it hands back a value. Actually, it's an IL value, and this is IL builder, but anyway, you get the basic idea. In JitBuilder 2, that becomes, I need to find some extension because it's the extension that introduces the operations that I'm going to work with. So I don't know how to do an add until I've got an extension object that tells me how to do an add. So now I call the operation on an extension object, and I pass it this location. So this is the code location that's causing this piece of IL to get generated. So I pass in its location, the builder object where it needs to get added, and then its operands. And then that thing still returns a value if it produces a value. If it doesn't produce a value, obviously it doesn't return a value. But so it's quite similar. The only difference is this kind of extension object thing got added in here, and the builder had to be demoted to a parameter that you send in.
Sorry to not let go of this yet, but the look, and I think it was better on your previous slide.
The location there, so this is still that source code location as opposed to where I am generating that add.
Correct.
From.
Okay. Correct. If you wanted to pass in that information, you would call something like the core extension arrow source location, and you'd encode the information.
Instead of located.
Right. You have to create there's actually a class called location. You create a location which describes your source code location, and then you use source location to inject that into the build project. Okay. So they're separate, totally separate concepts.
One question, and maybe this is, but does the builder actually build anything? Or
no,
okay,
not yet. Well, it builds. It's adding the operation to a list of operations.
Right.
But right now it's building IL. It's not actually like in JitBuilder. When you called add, it would translate that into IL at the OMR compiler level that, loaded the operation, loaded the left operand from the stack, loaded the right operand from the stack, issued an IA add in the case of the 32-bit integer one, and then stored it into a stack location, right? It would actually generate that IL in the OMR compiler, and then it would forget completely about it. Like you wouldn't be able to know what you'd done. All you have is this value that corresponds to the thing that you produced, but you'd have no idea that that thing produced a 32-bit integer, that it was an add operation, that it came from two other values. It was a straight pass-through operation. What's happening in this case is it's actually building up the structure of the IL in memory, and then you can process it later. So after build IL finishes, after all the IL has been built, that's like the corresponding thing in Testarossa would be ILGen. Right. Then you can do whatever you want with it. You can do analysis, you can run passes on it, you can optimize it, etc. None of that exists, but you could do that in principle. Well, none of it exists.
Yeah, I was just asking because the scope was actually doing all the loading of parameters and stuff.
Yeah,
it's curious whether there's more to Builder than it. I assume there is, but
there sort of. But I won't get into detail here, and I don't want to get distracted at this point with it. So we can talk later if you want. Maybe I can add it to part 2 or part 3. All right, so we covered this. Okay, so let's talk a little bit more about extensions because I've mentioned them a few times and brought up a few of them. So there are some extensions that already exist in JB2. The most basic one is core extension, which is, like I think I mentioned earlier, is automatically loaded into every compiler object. Compiler should be red and monotype font there. Some of the common facilities are things like Orphan Builder, which is a way of just allocating a builder object to start doing stuff with. Entry Builder is how you allocate specific. It's not very different, but it creates a builder specifically for the purposes of being an entry to a compile unit. JitBuilder 2 is not limited to having only single entry points, like single entry points and single and exits from things. But right now, all you can create are functions. Even in principle, functions could have multiple entry points, but nothing uses that, and it would not be able to generate code for it if anybody did specify more than one entry point. So, but in principle, multiple entry points are supported, so you could have multiple entry builders for a particular compile unit. Merge def is an operation that I don't want to get into detail on. It also defines a simple code generator compiler strategy, which all it does is try to invoke a code generator. So there is no code generator in the core piece of JitBuilder 2, but other extensions can load a code generator that will be dispatched when this code generator strategy happens, and I'll talk a little bit about that on one of the next slides. I mentioned the func extension adds support for compiling C-like functions. So function's a compile unit. It adds a function type, which can represent a function signature, which basically captures a set of parameter types and return types. Function context is a context that basically defines parameters. It has a place to store parameters and a place to store local variables, stack variables. Function scope is a scope that has a callable entry point, right? So that's why you can ask a scope for its builder entry, and it can hand you back something because it knows that it needs to have an entry point. So I guess I could say function scope is a scope that has it covers an entire function is the purpose of a function scope. you can associate smaller sets of builders with scopes as well. But this is what function brings in. Function symbol is a type of symbol that can be used to reference a callable function target. So you can call a function symbol or call using a function symbol basically to do a direct call to something. And then it adds specific operations. So call void, return void, load, and store. Actually, the function extension object itself doesn't directly expose the notion of call void, but it creates IL with the operations called call void. So if it has a call service that you can create. If you pass it in the right set of operations that has a return value, it will use a call. If it doesn't have a return value, it will produce a call void. So it kind of just differentiates a little bit between call that has a return value and call that doesn't have a return value. And the reason for that is so that the operation has the same shape, basically, from a number of returns point of view. And that
call is a direct call?
These are direct calls, yes. Okay. Load and store, I'm actually considering moving these into the core extension just because there's like symbol is kind of a not very useful thing in the core thing because you can't do anything with symbols. So the notion of loading and storing a symbol, even if you can't create a type of symbol in the core, it might make more sense for load and store to be there. But anyway, haven't done that yet. As I said, base extension is an extension that's more like, it provides a lot of the facilities that are familiar from JitBuilder. It's incomplete right now. It's not a full replacement for JitBuilder. It doesn't have all of the arithmetic operations defined. It doesn't have all of the, it has all of the types of JitBuilder plus function type. You can get access to other types, but and it creates all of the primitive types, it allows you to create pointer types, struct types, etc. As well as, it has some of the simple arithmetic like add, mul, sub, that type stuff. It has most of the control flow from JitBuilder 1, although it doesn't have switch right now. And a lot of the memory operations from JitBuilder 1 to be able to access fields from structs and to dereference pointers and to access arrays and things like that, plus a few pseudo operations that help simplify things like constant creation, etc. I'll mention it here because I do talk about it a little bit. I'm going to introduce this concept a little bit later, but it creates an add-on. So this is a dynamic extensibility mechanism. This is the first time you'll see it. I'll talk about it later in the talk, but basically it tacks some stuff into the compilation object. When a compilation object gets created, it creates some base extension specific stuff for managing the set of pointer types and a set of struct types that have been created for the compilation that you can access by a compilation object being passed around. It also does one for function extension as well. All right, more about that in a sec. Okay, so another change that's happened in JitBuilder 2 since the last time I talked to you, if you remember any of this. So the code base for JitBuilder 2 used to have a bunch of JitBuilder calls sprinkled throughout it everywhere. So every type and every operation knew how to make JitBuilder calls to produce code associated with those things. So to manage values of certain of those types, to create constants of those types, as well as the operation, like what does it mean to do an add, what does it mean to do a load, what does it mean to do a sub. All of that was sprinkled throughout the whole compiler, and I didn't like it, and I got annoyed with it, and decided that I wanted to have a JitBuilder extension where all of the details of JitBuilder were hidden away inside that extension, so that in principle, if you didn't want to use JitBuilder, or say you wanted to use the OMR compiler directly, or say you wanted to use LLVM, you could load an extension that would provide that support without having to have it all sprinkled throughout the code base. So you imagine if you would wanted to support the OMR compiler and JitBuilder and LLVM, then you'd have 3 copies of all of that code sprinkled all the way through the compiler, and everybody creating an extension would have to add their support into those things in order to be able to be generated by those code generators and so on. And so everybody would basically have to modify the whole code base all the time, which sucked. I didn't like it. So So the idea was that, or I wanted to explore the idea of encapsulating all of that within a JB extension, and then that was a forcing function on some of the extensibility mechanisms to be able to figure out how you could do that, and yet be able to deal with the fact that, well, maybe the base extension is loaded or maybe it's not. Maybe the func extension is loaded or maybe it's not. And how do you handle that? So, but the first thing that it does is it creates a code generator. So code generator is something that's defined in the core of JitBuilder 2, but it doesn't do anything. It just defines an API. So the first thing it does is it actually creates a real code generator object, a JB code generator object, and installs that as the one that gets dispatched. So that if anybody calls compile and asks for the code gen strategy, then it will end up invoking the JB code generator object. And in fact, if there were multiple extensions that created code generator objects, it could do all of them. So in principle, you could imagine a really interesting world where you load a JB extension and an LLVM extension, and it generates code for both of them, and then you can compare on the fly in memory what the differences are between those two things. Or you could run each one and compare the performance of them, or you could, you selectively do that for, whatever compile units you want. But for now, let's just imagine a world with JitBuilder. Also, when this extension gets created, it registers itself, and I'm not going to go into details on how it does this, but it registers itself to be notified when other extensions are created, so that it can watch and see, did the base extension get loaded? Did the func extension get loaded? Did the VM extension get loaded? And then if and when those extensions do get loaded, it can install specific add-ons like mix-ins onto they're actually called extended passes, but passes that can handle the IL generation for those extensions. All right, so the operations that base defines, the JB extension knows about the base extension, it knows which operations are in it, and it can it has a way of dispatching the JitBuilder calls in order to handle the IL for what gets created by the base extension, and similarly for the func extension, similarly for the VM extension. So I haven't talked about yet, but hang on to that for a sec. So the JB code generator object basically just walks over the intermediate language that gets produced as part of build IL, and it makes JitBuilder calls in order to generate native code by the OMR compiler. So the JB2 has been doing this forever, but it's now been kind of rearranged so that it actually does dispatching through the extension objects to be able to make sure that the IL gets handled by all these little objects that the JB extension is creating. This whole extension at some point will be supplanted by a direct OMR compiler extension. I don't know why there's no space there. So that it won't actually use JitBuilder as an intermediary, right? So JitBuilder is really just it's a very simple way to generate code that JitBuilder 2 leverages to generate code. But what should be really happening is that all of the code that's in JitBuilder that allows you to translate those code into OMR or Testarossa IL should really be in its own extension in JitBuilder 2, so that it can directly go to the OMR compiler code. And I think we'll have an ability to do that a lot better because it's really a code generation step. It's not a pass-through API. So you don't just see the API calls as they're happening. You see the whole. You can look at the whole code and know what's the best way to generate code for all of this stuff together. Anyway. Yeah, and then another one that exists is the VM extension. So this one I haven't had before, I don't think. But basically, it's the virtual machine state and virtual machine register and virtual machine operand stack and bytecode builder, which is all the facilities that make it easier to write JIT compilers and privatize basically the virtual machine state as you're writing the compiler. So the WebAssembly JIT, the John's T4 JavaScript thing, the Lua JIT, all of the JITs that we use leverage these kinds of facilities. The only one I haven't implemented is virtual machine operand array. Just like in the first time I built JitBuilder, it's left as an exercise for an intrepid contributor. But basically, this handles all the modeling on privatization of the state and ends up generating, IL that corresponds to the use of things like the operand stack without actually using the operand stack. And it depends on the base extension and on the function extension at some point. So, yeah, at some point I did have that comment here, but I also added this expanded on that point that was the last one on that thing. So there are some other extensions that are still under development here. There's complex, which is used to support complex values. I've had this in here for a long time, but it's not yet updated with the latest refactoring that's gone on, so it's not quite working at the current moment, but hopefully that should be fairly easy to get going. The debugger, the IL debugger that I created that motivated some of these abstraction layers that I was talking about has not yet been fully updated. I'm working on this right now as the sort of next thing that I'm going to get done. And then I have sort of some proposed things that I'm thinking about as sort of future directions here. So SIM is kind of like the core, some of the core functionality of debug, basically to help you. The idea here is that you could simulate the operation simulate what's going to happen when an IL operation runs, and provide ways for the compiler to figure out, for example, what a constant result. If you have an operation that has all constant operands and it has no external state that it depends on, what value does that produce? Do I want people to have to be able to express that in their description of that operation, or maybe the compiler can just figure it out by simulating what that operation is going to do? Essentially, you do a tiny little compile with just that operation and providing the operands that it's going to have, and find out what the answer is. That kind of thing. Obviously, that has to be done carefully, but but that's the sort of motivating notion there. A GC extension is one that I've been wanting to do for a long time, but just haven't gotten around to it. It's basically support integration with the OMR GC or another garbage collector. The idea would be to introduce a managed address type, which you could then allocate objects of, and that would be managed by the GC. And so you'd know to generate stack maps and other things, register maps, I guess, in principle too. This would require a lot of integration with the OMR compiler as well in order to get that working, and that's kind of not a path that I've gone down yet, but it's a direction that I'd like to get into. And then interpreter builder is kind of the big one that I'd really love to get to, which is essentially a compiler designed to simplify the creation of interpreters. So you start from something more like a virtual machine state description and a set of bytecode operators, and abstract away what's the structure of the interpreter, and have the interpreter builder, like this compiler, be able to essentially construct an interpreter and use it to even automatically generate a JIT compiler, because it knows what all the bytecodes do, and you get a simple JIT compiler out of it, or a simple tracing JIT compiler, or etc. And you could do you can generate different kinds of interpreters. You could do switch-based interpreters, you could do threaded interpreters, you can sort of make that the mechanics of actually arranging all of those things. You could do it all automatically, and then you could even design compiler passes, analyses / improvements that could enhance the design of the interpreter that specifically know that they're generating an interpreter. We've done some early experiments on this with JitBuilder in the past, but I think there's a lot more we could do there, and a lot more interesting stuff that could be done there, and then any others, of course. We do still have 15 minutes, so I'm going to do a very quick high-level overview of extensibility in JB2, some of which is fairly standard stuff, but the dynamic extensibility stuff and the support for dynamic mix-ins and extend passes that I talked about are referenced and talked a little bit about earlier. I'll give a little bit more detail on this, but for a detailed talk through this, I'm going to have to do another presentation because there's just not enough time to go through it all. So the static extensibility mechanisms are all just basically C++ mechanisms, and this is all fairly standard stuff. So, inheritance can be used when the new capability, if you're extending a compiler and you're creating a new capability and you're going to be allocating the new thing rather than the base class, then that's a place where inheritance is appropriate, right? So the examples here are function subclasses compile unit with the expectation that function objects are going to be allocated rather than directly allocating compile unit objects. And you use virtual functions all over the place so that even things that get past a compile unit can actually have their behavior overridden by what function defines and so on. The follow-on example is that the virtual machine, the VM extension, actually defines a VM function, subclass of function, with the expectation that if you're going to use that functionality, you allocate VM function objects, and that those are going to get allocated. Now, because the compile unit is a nice case because it's completely outside of the compilation, so nothing inside the compiler actually allocates compile units. It's things that the external user of the compiler are going to allocate. So there's no example within JitBuilder 2 where a compile unit gets allocated and then passed around. So there's you don't have to find some way of adding your extension capability into those kinds of objects. But that's not the case for everything in the compiler. So inheritance works where it works, but it doesn't work for everything. Similarly, composition can be used when you want that specific object and you don't really want it to be extended in any way. So the best example here is list, which just embeds a list object directly in something. And you don't really expect somebody to create a different kind of a list and want it to be used instead of that list. Static polymorphism, which we use in the OMR compiler in a variety of places, isn't specifically prevented, but not really favored. And that's mostly because I want this extensibility to be more dynamic in nature and not really statically locked in place. I don't want you to have to build it a particular way. I want you to be able to assemble the compiler that you want dynamically. This is probably not going to go well because I've been writing these slides very close to this actual presentation, but let's go through it and see if I can at least give you a flavor for how it works. If not, not how it works, how it gets used, or how it looks in the code base, as opposed to how it actually works. So there is a dynamic extension mechanism that allows you to add capabilities to existing objects. So even if the JitBuilder 2 allocates, I'm going to go right into the example, even if JitBuilder code allocates, for example, a compiler object as part of the compile process, it's actually doing a new new compilation object. So there's no way of adding anything to that compilation object dynamically because it's specifically allocating a compilation object. It's not sort of deferred to say, which type of compilation object would you like? You can do that, but it's a different approach to doing it. And in particular, you might not know, like different extensions might get loaded and some of them might need to add different things into compilation. So you don't want them to compete, right? So if the base extension wants to add something to compilation and the function extension wants to add something into compilation, inheritance becomes a really difficult way to manage that because you've got two things that, like, do you have both base and function? Do you just have base? Do you have function? What are you extending? So inheritance doesn't work very well. So JitBuilder 2 provides a mechanism, which I'm not going to go into detail on how this works in this talk, but it allows you to attach what I call add-on objects to existing other objects. And there's a way of registering to be notified of when certain things get allocated and so on. It's quite interesting, and it actually ends up being quite easy to use in the end. But as you might expect, there's some performance overheads to be expected. So it's not something you want to use arbitrarily or whimsically. But one example is the base extension, which attaches an object called a base compilation add-on to any compilation object that gets allocated. It creates a corresponding base compilation add-on. And in that add-on object, basically it includes some containers to maintain the set of pointer types that have been created and the set of struct types that have been created, so that across the compilation, you don't end up creating multiple copies of pointer to int32. And anybody can access those types by, if they're passed a compilation object, you can do this. So the first one is how it gets allocated, right? So when you allocate a base compilation add-on object, one of the things that gets passed in is the root object, the comp object that it's corresponding to. And then you can just do comp attach blah of this type, and there's some magic in there to say to recognize that it's attaching an object of this type, and this is it. And then later on, anybody who's passed a comp object, you can just do comp add-on and pass that type, and you'll get that object back. And you can only add on one of a particular type, so it's a little bit limited in that standpoint, but it's basically a way of saying, hey, associate one of these with this object, and then later on you can get the thing that you got out. So you have to know that you're using the base extension on both ends, but it can pass through a bunch of stuff that has no idea that there's a base extension loaded or that it's present. And so the extension objects, when they get created, they can register to get notified when things are allocated so that add-ons can be attached, etc. So it's kind of neat, and it's been hanging together for all the stuff that I did with JitBuilder 2 and with the base compilation, with the base extension so far. So I'm optimistic about this, but maybe when I go into more detail on this in part 2, we can have a bigger discussion about this. Another notion of sort of dynamic extension is this extended passes and how the code generator objects work for the JB extension. So when the JB extension gets loaded, it basically has a model of delegating the handling of IL components to the extension that introduces that IL component. So similarly to when you're building IL, you have to call to the extension object to say it's the base extension that knows how to create an add operation. That operation, when it gets created, also stores the base extension object on it, so that when other things pick up that operation, they can say, who's the extension that created you? And then there's a way of delegating an arbitrary service to that extension object using a similar kind of mechanism to the add-on notion, but it's slightly different. So I call them extended passes. And I created this one first, so I haven't yet figured out if I can collapse these two into the same thing, but they are slightly different too. Let's see. Do I really want to go into detail here? It might not be the right moment because we're kind of at the end of the talk. I've been going for quite a long time here, so maybe I'll just defer this to say there is this notion that you can do this. So this is how the JB extension, the JitBuilder extension works. That it uses this facility to delegate the handling of code generation to the various extension objects, but I won't go into any more detail than that today. I have two more topics to kind of cover quickly. I've talked about both of them previously, but I just wanted to remind everyone about the integration that I have done so far for OMR. So all of this right now builds against, uses the OMR build system in my private copy. So the way that I did this was I took the JitBuilder code base, which is a compiler extension in the OMR compiler, and I made a separate copy of that called JB2, which allows me to evolve JitBuilder independently of the actual JitBuilder that other people might depend on. I haven't had to do very much of that, so it might not be necessary, but anyway, I've done it. And then I took out anything that wasn't specifically needed for JitBuilder 2, which is basically the core JitBuilder API. I created an API specifically for JB2 under it, which I called API. Not very imaginative, I know, but that's where it is. And then all of the JitBuilder 2 implementation is underneath API, and then underneath, so the core stuff is all in the API directory, and then there are directories for each of the extensions underneath that. So base, func, VM, core, all of that stuff are actually core extensions, not. It's in the main API directory. But and then I added a build flag OMR JB2 to the CMake so that you can build it. Right now, JitBuilder 2 just builds everything that's there. So it includes all of the extensions. Probably should have their own things, but it doesn't right now. Also, each one of the extensions has, except for func right now, has tests that are written against them that try to test a lot of their functionality. So base does 242 different tests of various combinations of things that it defines. It's not complete, but it's better than nothing. And it automatically adds those tests into the build, so that if you run ctest, it runs. There's about 6 of them that run at the beginning, and right now I've got it set up so that it runs every one of them under Valgrind to verify that there are no allocation leaks at all through any of the tests. So it took me a while to get there, but but they all are currently running with no allocation leaks whatsoever. and it continues to test those. It runs them under the sort of very, I forget the name of the option, but it's the like extra detailed leak checking runs that it does. It takes about 15 seconds to run the base test because it's the biggest one. And just as a couple of side notes, I've used a different code format for JitBuilder too. Kind of like I was testing out sort of, I guess, how I liked the code format that we talked about in one of our earlier designs. So it uses 4 spaces and it doesn't use the curly brace on a separate line approach and stuff like that. Anyway, I'm quite fond of it, I would say. But I also didn't find that it was like it didn't take me long to adjust one way or the other, so it wasn't like a magical productivity enhancement for me, but it was but I do find the code structure to be quite nice. Anyway, and right now extensions are all very Linux focused, so it's libdl is being used as the thing, so it's not exactly cross-platform at this point, but you know, these are things that could be enhanced, obviously. And I did talk about one of my previous ones about maybe moving away from STL containers, so I've taken overt steps to move away from STL. I don't know why list T isn't bolded there, it should be. So I've converted most of the internal STL container use to using an internal implementation that I wrote and that I have wrote tests against. So there's the list, there's an iterator class, there's an array class, there's a string class, which is still backed by a standard string, but it's a lot easier to replace now because there's only one, the string only appears in one place. And the only one that I have not tackled yet is standard map, which is going to be a fun one, but I'll get there eventually. I just haven't peeled that one out yet. So just to give you a flavor for how the iteration model works, the iterators are passed around by value, and they actually create a copy of the list that they iterate over. So the iterator can you ask for an iterator. If it has item, you can continue, and then you can ask for the item, and basically gives you back the thing that you're supposed to get. So the template handles all of the classes, and it feels pretty clean to me as a notation, even though it's not exactly the same as what the STL containers used or that anybody else uses.
Is there a plan to have mutable container iterators, or is it something that you think is not?
It could be done. I mean, I'm actually not 100% sure I was correct right now that it copies the iterator. I know it does in certain cases, but I'm not sure that it does in all cases right now. I'm pretty sure I copied things because I didn't want them to. I wanted them to be immutable, but it also does. It also does automatically detect if the underlying container changes between when you allocated the iterator and when you access it. So every time you access the iterator, it goes back to the base container and verifies that it hasn't changed. And it does that by basically every time it changes, it increments a counter inside the container, basically, and then it just caches the value when it created the iterator, and if the values in the container is different, then it knows it's changed, so it's been mutated.
But I mean, how would you mutate it if you didn't have an iterator?
That's a good question. I mean, in principle, you can call things to remove an item from a list that don't rely on its position, right? So you can do things like that. But to be honest, there aren't a whole lot of things in JitBuilder 2 right now that mutate. They create right now. We're in the process of creation. All right, and that's finally right on time. The end of part 1. So I have an intention to come back with a part 2 where I'll talk more about allocators and go into more details on the dynamic extensibility, because I think it's a pretty interesting area and I didn't have time to cover it very well. And in fact, I wrote this slide 3 minutes before the start of this presentation. So you can tell how quickly I put some of this together.
Okay. All right, thanks, Mark. We'll pause there for questions.
Yeah, sorry, I didn't intend to take up all of the time. So if anybody wants to reach out to me with questions, I'd be happy to get into discussions with this offline, or we can leave it till the next one of these and get more. more questions answered.
No? Okay, well, if there's no questions, I want to thank Mark for a very good introduction to JitBuilder 2, and we'll look forward to part 2 in the coming weeks, months?
Weeks, hopefully.
Yeah, okay, awesome.
Hopefully.
All right, thanks everyone for attending. See you next time.
Thanks.
Bye.
Everybody.